It's almost gentle in the way it releases the slug out of the collet. That's awesome.
Dr. D-Flo.
Hey, what's up guys? It's Dr. D-Flo and I'm back with another upgrade to my CNC mill that I think you're going to enjoy. But first, we need to talk about how I change out tools between operations. When I first got the mill, I received a set of R8 collets. For this type of tool holding, there has to be an exact match between the collet diameter and the tool shank diameter. Tools could be as small as 1/8 of an inch and as large as 3/4 of an inch. As a tool change example, we will use this 1/4 inch mill drill and 1/4 inch collet. This is the drawbar. It threads in to the bottom of the collet, sucking it up into the spindle. Now the taper on the collet will cause it to close down on the end mill. I start off by getting everything finger tight so that the tool doesn't fall and hit the table. Now this Precision Matthews 833 TV mill has a major design flaw. There's no spindle brake or flat on the spindle nose that I can grab onto to stop it from spinning when I'm tightening the drawbar. Precision Matthews has been relatively quiet on this issue, and I think they suggested using a rubber wrench to stop the spindle from spinning. Now this rubber wrench is too big because I don't actually use this method, but I guess it would work, albeit it would be a hassle. I've opted for the more dangerous approach to tightening the power drawbar, which is turning the motor on a low RPM to oppose the tightening of the drawbar. Here we have it at just 50 RPMs. However, if I accidentally turned off the motor while it was still set to a high RPM, that would be an incredibly dangerous situation, right? The wrench could fly off the power drawbar, or I could get sucked into the mill. Neither of which are good. So besides this motor method being dangerous, it's also not very repeatable when it comes to the holding force of the tool. I've actually had a couple end mills get pulled out of the collet because the cutting forces were too high. People have semi-automated the tightening and loosening of the drawbar with an electric or air-powered ratchet. This method would result in a more repeatable holding torque, but it wouldn't work for my mill because I still don't have a way to prevent the spindle from rotating when tightening down the drawbar. And I'm not using a rubber wrench. A pneumatic or power drawbar is a much better solution for my setup. If you're not familiar with a power drawbar, it'll make more sense when you see it in action. But briefly, here's how it works. An air cylinder presses down on the drawbar to unseat the collet when you go to change out tools. And when you're ready to cut, springs pull the drawbar up at a constant force, bringing the collet into the spindle, securing the tool. I initially had plans to put together my own power drawbar, but the build requires a longer drawbar than I already have. I don't have a lathe to turn down such a part, and it was actually more economical to purchase a kit from Priest Tools than to have the local machine shop make me a drawbar. Also, Greg from Priest Tools has already worked out all the physics, so we should have the perfect amount of holding torque for this mill. Let's meet over at the bench to talk about all the components that make up a power drawbar. So here's everything that comes with the kit. We've got bolts and spacers, mounting plates, a switch for turning on the drawbar, which is connected to a limit switch, more on this later, and also an electric solenoid. We have some tubing, we have the air cylinder, we have Belleville Washers, a collar, a new drawbar, and some anti-seize lubricant. The air cylinder might be the most important part. This is a 2-stage air cylinder with a 100mm bore. With a 2-stage air cylinder, you get much higher forces and a more compact design. If you've seen other videos of people installing power drawbars, they often have to include a lever arm to amplify the force of their cylinder. We don't have to do that for this cylinder, which simplifies the design. I'm actually going to hook this air cylinder up really quickly just to show you how it works. So both of these tubes connect back to the solenoid. And this clear tube will connect to my compressor. Here's the hose for my compressor. The air is at 120 psi. Now this cylinder will work at 90 psi, and it'll just be able to apply less force. When I flip this switch to the on position, it lights up, but nothing happens. That's because the limit switch also needs to be pressed. This is a safety feature, and I'm going to talk about where it goes in the assembly later on. But I'm going to go ahead and click this with my finger. And as you can see, air is supplied to the cylinder, and it rises up out of the housing. When I release the limit switch, the solenoid cuts out, releasing air out of the cylinder. Now this is a single acting air cylinder, so it needs to use gravity or a spring to bring it back down to the start of the stroke. That leads us to our next component, the Belleville washer. Believe it or not, these conical shaped washers are very powerful springs. They are more useful when stacked with other Belleville washers. You can stack them in parallel, where they are all facing the same direction, or in series, where they alternate directions. In a parallel configuration, you can get a stiffer joint, but maximum deflection of the entire stack equals that of a single Belleville washer. In a series configuration, the amount of deflection will scale with the number of washers. The series configuration is particularly useful when you want a lot of travel in your spring joint, which we do need. I do want to point out that you can get almost an endless number of spring constants and deflection amount by stacking them in combination of both series and parallel. Greg's already done the math for us, and we need 8 Belleville washers stacked in series. This will give us enough deflection that the collet will pop out of the spindle and release the tool, but it will be stiff enough for up to 34 foot-pounds of holding force. We will cap off this stack with a little collar, and I will talk about the function this collar plays in a second, but let's go ahead and install the new, longer drawbar on the mill. So we need to remove the faceplate and the sheet metal up here that's protecting the belt drive. You actually have to lower the quill to get this piece out. We'll remove the current drawbar and collet. Applying the anti-seize is a little bit messy, so I'm going to throw on some gloves. Start by putting a little bead of the lubricant on the head of the drawbar. With these Belleville washers, it's kind of hard to see their concavity until you start stacking them in this series configuration where there's a little bit of space in between each unit. This space will be taken up when the stack is compressed. The last component that needs some anti-seize is the collar. We'll flip the whole assembly upside down. All right, so I went ahead and switched gloves. We need to rub a little bit of anti-seize on the outside taper of our collet. We want to be really careful not to get the anti-seize on the inside of the collet because then our tool will slip. You want this collet to be able to pop right out when the air cylinder presses on the drawbar. We got a nice light coating on there. Go ahead and switch gloves one more time. Now, this next step, we're going to pull the collet fully up into the spindle, and we're going to actually set the holding force. So we need to insert this slug because you don't want to compress the collet without a slug in it because it'll stick. Okay, that's finger tight. These are the instructions that came with the power drawbar kit. We got the drawbar hand tight, but now it's time to tighten it down further and compress those Belleville washers to get significant holding torque. This table right here tells us how much holding torque we get for each 1/6 of a turn of the drawbar. I'm going to shoot for 2 full turns to get 32 foot-pounds of torque because I do have 120 psi compressed air. So once I took off the cover, I noticed that the pulley has some indents for a spanner wrench so that I can hold on to that. I was worried at first I was going to have to use that rubber wrench to set the holding torque, but fortunately I don't have to do that. Keep an eye on this spacing. You should see it compress. Yeah, so that's 1 turn. That's 2. You can definitely see that that space got much smaller. Those washers are being compressed. And in turn, we're gonna have a lot of force keeping that collet and that tool where it's supposed to be. Next, we need to install the base plate. The other components will attach to this. Another awesome feature about this kit is that it uses the existing mounting points so you don't have to drill any new holes in the casting of the mill. Next, we need to do the cylinder assembly. We're going to head back over to my bench to put that together. So the cylinder attaches to this plate. Through these big bolts and spacers. I think these other holes are for if you opt for the smaller cylinder. I thought it was symmetric there for a second. This edge is actually slightly longer and it should be next to the air inlets. Are you kidding me? My 3/8 Allen key is not big enough? That's probably a 1/2 inch. I don't keep that on hand. I'm gonna have to purchase a 1/2 inch for later, so hopefully finger tight will do for now. So now we need to attach this assembly with these bolts and these 2 black spacers to the base plate. This is going to look a little bit funny with only one side having spacers, but it'll all make sense in a second. So here's the weird part. This whole assembly is floating. And trust me, that's by design. You don't want the force of the cylinder translating to the bearings that are within the spindle. They're not meant to withstand that kind of an axial load. So here's the trick. This plate slides into these dovetail grooves and goes around the collar. When the air cylinder presses down with its force, this is going to pop up. But it can only go up so high because this piece is trapping it. So effectively, you're just pinching this area. The force is restricted right here, and the spindle bearings aren't going to feel any of it. It's ingenious. It's really awesome that you can take a mill without a power drawbar and retrofit one with a relatively simple assembly, and you can reap those benefits. It's really cool. I hope you can now understand why this plate, which is known as the actuator plate, is so important. If it's not present, if it's not engaged underneath the collar, when you turn on the power drawbar, that force will be translated to the bearings. Now, to prevent that from ever happening, this kit has a trick up its sleeve. Remember that limit switch from earlier and how I said it was a safety mechanism? Well, the electronics are set up in such a way that the power drawbar won't actuate unless the limit switch is triggered. And the limit switch can only be triggered when the plate is fully engaged. I'm going to go ahead and install that now. I love it. It's idiot proof. When you're working on a part that requires like 20 different tool changes, your mind is going to be preoccupied. And it's nice that, if you forget to engage this, the power drawbar is not going to turn on. We can go ahead and attach the rest of the electronics so they can stop dangling. The nice part about this manifold that I set up in the last video is that these two outlets are unregulated, so they're going to be at 120 psi. So we can adjust this bolt that's screwed into the shaft. We want it to be just above the drawbar so it's not rubbing when it's spinning. All right, it's time to flip the switch, and hopefully that aluminum slug will drop out of the collet. Here we go. Yes, that's awesome. Will it grab it? Yep, no problem. Let's do it again. It's almost gentle in the way it releases the slug out of the collet. That's awesome. Man, this is obviously way safer than the motor method. It's way quicker. It's awesome. I don't know why it took me almost a year to do this upgrade. Sweet. I just need to still tidy up all of these tubes and the power cord for the drawbar. I'm going to save that for a later date because I just want to keep rolling with this project in this video. The one downside of the power drawbar is that it's much more difficult to switch between R8 collets. You would have to reset the compression on the Belleville Washers every time you wanted to switch to a tool with a different shank diameter. But there's a solution. Enter the Tormach Tool System, or TTS for short. Perhaps you thought you'd be able to avoid paying the Tormach tax if you went the DIY route. Unfortunately, these tool holders are just too good to pass up. Their operating principle is simple. One end is a 3/4 inch shank and the other end is a tool holder. You have a couple different options for holding the tool, from an ER collet to a set screw holder and even a Jacobs drill chuck. To be clear, I'm in no way sponsored by Tormach. I'm just highlighting an invention that made CNC milling with an R8 spindle way more convenient, because you can rapidly switch between tools without having to switch out the collet, because all TTS holders fit into a 3/4 inch collet, which is the size that is currently installed for my power drawbar setup. Check out how quickly I can switch from a roughing end mill to a finishing end mill to a drill. It's a little tight. The TTS holders are a natural pairing with the power drawbar. If you've seen some of my past videos, then you will know that I have been using the TTS holders for quite a few projects, even without the power drawbar, because these holders allow for repeatable tool offsets when you're swapping tools in and out of the spindle. For the second part of this video, I wanted to give an intro to setting tool offsets. Just FYI, this section is aimed at the beginner and will not cover the extra precautions needed for high precision work. When you first start running your CNC mill or even CNC router, you usually set your Z0, which is typically when the end of the tool is touching the top of the stock material, by placing a sheet of paper or a feeler gauge on top of the material and lowering the Z-axis until you feel resistance when you tug on the paper. You can account for the thickness of your feeler gauge or paper to find Z0. There are two problems with this approach. The first is that it is subjective because your definition of resistance may change from tool to tool and stock material to stock material, which affects accuracy. The second problem is that this method is slow. The quickest and most accurate way to find Z0 is to touch off the top of the stock material with a digital or analog probe and then compare the length of the probe to the length of the next tool and add or subtract distance accordingly. Now, what is length referring to? We need a reference point to measure our tools from. The most logical point to measure length from is the bottom of the spindle nose, because this point is accessible and its position is always known after a homing cycle. So the length of the tool will actually include part of the TTS holder or the body of the probe. Our first objective is to find the length of the probe. This can be a little tricky because we don't need to know the static length. We need to know the length of the probe when it detects an object in the Z-plane, which means the probe length will be slightly shorter than it is now. There are a couple different ways to find the probe length, some of which don't require any fancy tools. The only wrong way to set the length would be to touch off the probe tip on the touch plate. This would result in an erroneous probe height because both the touch plate and probe move, and it would be impossible to know how much movement was a result of the plate versus the probe. I personally use this analog touch plate to find the probe length through the following process. First, I use a gauge block to bridge the post on either side of the touch plate, depressing it in the process. I set the indicator to read 0 at this point and then remove the gauge block. Next, I bring the spindle nose down until the indicator reads 0 again. The spindle nose is now at the height of the post. I will set this as my reference point and record the absolute machine coordinates. I will then load my digital probe into the spindle and have it find the Z height of one of the posts. This will change the offsets in my G54 coordinate system, but I can recheck the machine coordinates for the new Z value, which can be compared to the Z value from when I touched off the spindle nose to find the length of my probe. With this method, there's only one moving part. Now, because you have to own a manual tool setter for this method, you could also use this instrument to find the offsets for your tools, and it really doesn't take that long. This is the reason I say the digital touch probe is not mission critical. However, I do find the digital touch plate to be convenient, so let's go over that process quickly. Similar to the analog touch plate, we bring the spindle nose down until the touch plate alarms. This is the reference position, and from there we can touch off tools one at a time. For each tool, the software compares the Z position of the tip of the tool to the spindle nose to find the tool length. Each tool length is stored automatically in a digital table, which prevents any transcription errors that can occur when you have to manually enter tool lengths in a table. I leave a little note next to each tool so I don't confuse them. The digital touch plate is always sitting on the table, even during cutting operations, and chips will stick to the top of it. If the chips are not cleared off, then the next time a tool is touched off, the wrong length will be calculated because what was measured was the length of the tool plus the thickness of the chips underneath it. To automate the cleaning of the touch plate, I installed some pneumatic tubing that will supply a blast of air prior to touching off the tool. The air is controlled by an electric solenoid that I have mounted in the back. I will upload the macro file and wiring diagram to my website if you want to try out this upgrade for yourself. If you're thinking about purchasing, building, or converting a mill, then I strongly suggest checking out my CNC mill webpage. I've spent a lot of time writing down everything I've learned from my conversion to share with you. And with that, I'm going to catch you guys in the next video, which may or may not be my next planned CNC mill upgrade. You're going to have to subscribe to find out. Have a good one.